So last lesson we were looking at using limit theory in order to show that we can in fact find the gradient of a function at a very specific point. And we used f of x plus h minus f of x over h, and that was called first principles. And what we were left with is this thing called f dash of x, which we call the gradient function. And a more formal language for that gradient function is we say that this is the derivative of f of x. So we say f dash of x. So f dash of x is the derivative of f of x. The derivative is the gradient function of the original function here. What we also probably discovered, unless you've got a high tolerance for pain, is that using limit theory in order to work that out, the gradient function, the derivative, was a major pain in the bum. So to cut a long story short, if you had a look at how the gradient function works and the limit theory works, we always end up reducing, if for a polynomial at least, we always end up reducing the powers by one when we come out the other end and have a derivative. So some very smart people had a look at this in more detail, and they examined what the effect was of finding the derivative, and they came up with this thing called the power rule. And it's going to be the major basis of finding a shortcut to finding the derivative for this year. There are a whole bunch of different rules or methods for finding the derivative. This power rule really only works for power functions, which are functions which kind of look like that. So a polynomial function is an example of a power function. So is 1 on x, so is square root of x. They're all power functions. I'll let you think about why they are in a second. And they all work the same way, which is really handy. And that is that if you've got something like ax to the power of n, then the derivative is quite a simple little process. A stays where it is, but then the n gets brought down in front, and then we keep the variable as is, and then we subtract 1 from the variable. So n goes down, and then the power gets subtracted by 1. Let's have a look at that in practice. So we're still looking at the first slide there, the first quarter. So if we have f of x equals 3x squared, then the 3 stays there. We multiply it by 2, and then we multiply it by x, and we subtract 1 from the power. So it's 2 minus 1. And so we end up with 6x to the power of 1, and we don't bother writing the 1 in, because anything to the power of 1 is just itself. And so that's the derivative. Now, in practice, we would never write that. We would just go, 3 2s are 6, x to the power of 1 less, so x to the power of 1. So you would just go straight from that to that. So if f of x equals 3x squared, f dash of x equals 6x. The derivative function is 6x. The gradient function is 6x. It works across a whole bunch of things. Looking at the next slide there, slide 6, I might even just zoom up so we can see it a little bit more easily. So it works for constant functions. So a constant function, for example, is f of x. And if you think about it, if I just draw that as a graph, like so, f of x equals 3 would be like this. And what's the gradient of that function? Well, the gradient's it is neither positive nor negative, so therefore the gradient is 0. So if f of x equals 3, f dash of x equals 0. That makes sense. But why do I say it works for constant functions? Well, because we could, if we wanted to, it doesn't really make sense, but I'm going to put it anyway. I could put x to the power of 0 there as my variable, 3 times x to the power of 0, because x to the power of 0 is just 1. And then what I'm doing here is I'm going 3 multiplied by 0 multiplied by x to the negative 1. And this bit would equal 0, and anything multiplied by 0 is 0. So it kind of works. It doesn't, it's a bit of a fudge to show you that, but I'm just saying it basically does follow suit. It also works for linear functions. So again, if I draw the graph of that, then we would have something like that for f of x equals 3x, and the gradient is constant, isn't it? It's positive. It's constant. It's not increasing or decreasing, the gradient I'm talking about. And we would have f dash of x is equal to 3. And we know that because we've got a linear function. We know that this is the value of m. But it's nice to see that derivatives work as well, because this is 3x to the power of 1. And so my derivative rule says take the power down. So it's 3 times 1, multiply it by x to the power of 1 less, which is 1 minus 1. So that's x to the power of 0, like I set up here, is just simply 1, and 3 times 1 is 3. So that makes sense. Let me color code that back into black. Okay, it also works for higher powers as well. I just thought I'd just give one more example where it's a little bit more slightly complex. And let me just skip the steps a little bit so we can sort of see it. So the value before the variable just stays there, the coefficient 2/3. Bring down the power, that's 3, and then reduce the power by 1, so x squared. And you can see, I hope, that I could cancel out the 3's here, top and bottom. And so this would be equal to, oops, get the right color. This would be equal to 2x squared. So 2/3 x cubed is f of x. The derivative function f dash of x is equal to 2x squared. Okay, I'll zoom out now so we can see it all at once, and I'll go down to what is called slide 7 there. We're going to look at negative powers in the next video, but very, very briefly, if you have the variable on the bottom of a fraction, we can always bring it up to the top, because remember that 1 on a to the power of n is equal to a to the negative n. That's why we did our index law review last week, or the week before. And we can now apply the rule exactly as we usually have. So we've got, what is f dash of x? Well, we bring down the number before it. There's no coefficient in this case, or the coefficient is 1. So we've got -2, and we subtract 1 from the power, like so. So we've got -2 x to the power of -3. So just be mindful that we have gone down a power. But if I write this now as a positive index, that would be -2 on x cubed. So the x to the -3 has gone down to the bottom here as x cubed. So it looks like we've gone up by a power, but we haven't really. It's still consistent with everything we've said about finding the derivative, because really we've gone from a -2 power to a -3 power. So keep that in mind, but we'll have a look at that in more detail in another video. It also works for fractional indices, and I'll just do this really briefly because I'll do some more detailed examples later on. So just remember that if I've got a to the power of n over m, it is equal to the nth root of a to the power of n. I've got the square root of x cubed here. I know it's the square root because there's no number in here. And so I can rewrite that as x to the power of 3 on 2. So that means f dash of x is going to be 3 on 2. I'm bringing down the power, and then I'm going to subtract 1 from the power, like so, which I will just work through. So it's going to be 1 over 2, like so. So 3 over 2 minus 2 over 2 is 1 over 2. And I can write that in a few different ways. I could write that as 3 root x over 2, or I could write it as 3/2 root x. Both of those things would be appropriate ways of writing it. Okay, so it does work across any kind of number that is in the power. So if we have a look here, in this slide, the top left-hand slide here, I'm just pointing out that the rule works if you've got it broken into different parts as well. So like basically a whole polynomial. So you've got 3x to the 7 plus 4x cubed minus 2. So all you do is you apply the power rule to each part, like so. So we would, if I color code it a little bit, I'll probably run out of colors, but this would become, well, 3 7s are 21, and then x to the power of 6. And then we've got 4x cubed. So same thing again. We'll go 4 times 3 is 12, and then subtract 1 from the power, so it's 12x squared. And then we've got minus 2x. So remembering that we've got 2x to the power of 1. So I will then go minus 2 times 1 is 2. Choose the right color, is 2, and then the x disappears effectively because it's x to the power of 0. And then the minus 100, that's just a constant. So the constant term always disappears because this turns to 0 effectively, if you remember back here. If it's a constant, the derivative is 0. So you always get this idea that the derivative function, the gradient function, is always 1 power less ultimately than it was to start with. Do note though, down the bottom there, it does not work over multiplication. So you cannot go that the derivative of x squared plus 3 times x to the power of 5 minus 2, you cannot go that's 2x multiplied by 5x to the power of 4. That would be a no. Okay, you cannot do that. It only works over addition and subtraction, and I'm not even going to explain why. I'm just going to say that that's how it works. Now, a couple of last things before I wrap up this video. How would I solve that problem? I would have to expand it first. So I would use some sort of chicken beaking method or whatever you want to do, and I would go that's equal to x to the power of 7 because I'm adding my indices together there because it's the same base, and then minus 2x to the power of 2 plus 3x to the power of 5 minus 6. So that's a straight expansion. Nothing too dramatic there, I hope. Running my numbers a bit clearer. I might just write it in descending powers because it makes me feel better. And then I'm going to work out what the derivative is, the gradient function, by using my usual method. So bring down the 7. So I've got 7x, 1 less power, 7x to the power of 6, plus 3 times 5 is 15, x to the power of 4, minus 2 times 2 is 4, x to the power of 1, minus 6 goes down to 0, so the derivative function is 7x to the power of 6 plus 15x to the power of 4 minus 4x. I could try and factorize that if I wanted to, and if it was valuable to do so. Okay, two last little things. Number one, there are two notations for the derivative or the gradient function. One is f dash of x, and it's most frequently used when you're starting with f of x. You just go f dash of x equals. If you start with y, you're going to use this notation here, which is dy by dx. This is called Leibniz notation. And I'm looking at my textbook now because I just want to make sure I'm spelling it right. If not, I'll have to have a bit of a bit of a stab at the spelling. I'm pretty sure it's this. I'll correct it later if I'm not right. But it's named after a guy called Leibniz, and I quite like it because it corresponds to how we've been talking about rates of change. Remember, I got you originally to talk about dy by dx. That was like, change in y over change in x, and delta reflected this idea of the change. So in the lowercase for delta is written like this, roughly, in Greek, like that, and the English equivalent is d, like so. So what this really shows is it's saying this is small change in y over small change in x, which is exactly what we do with that limit notation, dy by dx, little change in y over a little change in x. Okay, so the last thing to look at is, and you know what, maybe I'll change this to y notation just to make it different. The last thing to look at is what happens if we're asked to find a specific value. So if you're asked to find a specific gradient, say what is the gradient of the function at x equal to 1, the first thing we would do is find the derivative. So we would go dy by dx is equal to a half. You could do this in your head. I'm just spelling it out a little bit. X to the power of 1 minus 1 x to the power of 0, so that's just minus 1, and the plus 1 disappears. The constant always disappears. Simplifying that, I would get 2, oops, that'd be wrong, wouldn't it? Half times 2 is 1, so it'd be x minus 1. That is the gradient function, and now we want to know what happens at x equal to 1. And so we substitute in. So we can go at x equal 1, dy by dx is equal to 1 minus 1, which is equal to 0, i.e. the gradient is 0. Now, I'll leave it with this little thought. If this is the original function, which is a quadratic, like so, a quadratic function, what does a gradient of 0 mean? We'll explore this in a later video.